Let's talk about the Naked Mandelbrot. You'll see a view of the Mandelbrot that you've never seen before. We're going to begin by defining a complex plane. We're going to use an Argand diagram to define a plane that consists of both real numbers as well as imaginary numbers. Notice there's an elephant in the room here we'll talk about later. The imaginary numbers have I associated with each number. What is I? I is the square root of -1, and it makes it imaginary. And that's all we're going to say about that for now. Real numbers obviously do not have that I because they are real numbers. And when we pick a point on the Argand diagram, such as this point right here, what we're doing is we're picking a complex number that consists of a real component and an imaginary component. So if we pick 7 as the real number, it joins with -4i on the imaginary line, coming together to have the complex number 7 minus 4i. Likewise, if we picked 3i, and then we selected -5 on the real number line, we would come up with a complex number -5 plus 3i. Now, with regard to the circle of radius 2, the reason why we haven't talked about it yet is that this is where Mandelbrot lives. This is where Mandelbrot did all of his work. He didn't care about this part, this part, this part, or this part. He lived within a circle of radius 2. Now, what do you think Mandelbrot did within this circle of radius 2? He experimented with picking points. Just like we picked points earlier, he picked complex numbers within the circle of radius 2. He picked numbers between 2 and -2 on the real number line. He picked numbers between -2i, +2i on the imaginary number line. And when he picked them, he noted the results. And he noticed some very interesting patterns developing. Very interesting patterns. Let's take a look at the pattern that he started to see. He picked points out here, and they came back black. He picked points here and came back red, darker red, salmon, green, all kinds of colors. I thought that was fascinating. This was his world. He wanted to find out more about it. And so do we. But the question you should be asking yourself is, where did all this information come from? Just because he picked a point, how did he know what color it was? How did he know that this was a shape like a baby? Where did it come from? All he's doing is picking points, and something is telling him, or telling us, what color to make it. It was Mandelbrot's recursive equation that was giving him all this information. Let's look closer. He came up with an equation that if you fed a number into it, it would tell you whether it's background. It would tell you whether it's a set member. We'll talk about what that means. Or it would tell you whether it's a fractal or not. So he came up with this equation, and he started feeding points into it, and it started talking to him, telling him what colors to use, telling him what kind of point it was, whether it was a fractal, whether it was a set member, or whether it was just plain old background. And I'm sure he was amazed, just like we are. What possible kind of mathematics in there could give this kind of information? So let's take an example. This is a point. Notice we got 0 plus 1i. Well, there's 0 real, plus 1i. It's right there. So that's 1 point. There's another point, 0 plus 1.2i is right there. And this point is 0. That's where the real number comes. The 0 minus 0.4i. Notice these are all small numbers because they're all within 2, smaller than 2. So we pick 3 points, and we send these 3 points to Mandelbrot's recursion, and it comes back and it says, gives us information. It says, this is a background point, and it's red. We say, okay. Notice it told us it had 2 loops in it. Fine, that's how it knew it was background. So we put a red there. And we fed the second point into it, and it said it's 43 loops. It's a fractal. It's green. So we put a green there. And we fed this point into it. Comes back, it says it's got 1,000 loops. It's a set member. Let's make it bluish or purple. And we'll do that right there. Notice we don't have any information what this is. We don't have any information why it's red, blue, or whatever. All we know is we pick a point. And this box tells us what to color it. Well, let's not stop with 3 points. Let's pick some more. This is 0, positive 1.2i. That's this one right here. Picking that point is the next one. So this line is inverse compared to this one. But so as we go down there, we'll be going up this way. And so we pick all these points and we send it to the recursive equation. The recursive equation comes back and tells us this, that this one, which is this point right here, has 2 loops, and it qualifies as a background point, a red point. This one has 43 loops, and it's a fractal. It's green. This one is red, only has 17 loops. And then we get into an area where we have 1, 2, 3, 4, 5, 6, 7 set members. Blue, purple. 1, 2, 3, 4, 5, 6, 7 set members. And then another background, another fractal, and a loop 2 with more background. Well, you might say that's fine. Okay, we get some information back, but where are we going with this? What are we going to do? Well, let's not stop now. Let's feed some more points into it. Let's feed all these points into it at minus 0.8. That's what this is all about here. And as we fed these points into it, notice there are no significant numbers except this one. These are all backgrounds, except for right on the number line, which is a set member, which is that one right there. That 1,000 is right there. These are all backgrounds. So that's a little bit more information. Let's pick minus 0.4. That's what this is. These are insignificant. These are all less than 40 or less. And there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 set members right in the middle. Remember we had 7 over here, and then we got 5, we got 1. There's definitely a pattern developing, and that's the kind of thing that Mandelbrot first noticed. Because remember, when Mandelbrot was doing this, he had an IBM 370 computer back in 1980. He didn't have immediate response like our desktop computers of today. But still, when he put this to a line printer and he started to see this pattern, he proceeded on. This information here, we have already done that. That's the one on the 0 number line right here. We already did that one. It's got the 7 set numbers here. The only one we haven't done yet is this positive 0.4. We fed that into the recursive equation, and there is nothing above 40 that comes back. It means that whole line is nothing more than background. Is there a pattern here? See the big scheme of things. We can start to see that the blue kind of gets into the blue area and the red gets into the red area. And yeah, there is a pattern. Keep in mind. And we're doing this. You know, we did this. This is difficult, tedious work, but we're finding out information. We're seeing something start to form. Now we get serious just a minute. And let's pick a higher resolution. That is, let's pick 12.5 dots per unit and get serious and try to see what kind of pattern we have here. And keep in mind, this is 2 units here, 2 units here. That's 4 units across, radius of 2. There's 50 dots across. That's 12.5 dots per unit. And we start to see that, yes, in fact, there is what looks like a Mandelbrot developing here, along with this red layer here and the black surrounding pad, if you will. But let's not stop here. Let's make those dots smaller. Let's get a higher resolution. How about resolution 0.04? 25 dots per unit. It's starting to become clearer. 100 dots per unit. 1,000 dots per unit. Much clearer. Keep in mind, where we're going with this is that we have a circle of radius 2 that is made up of dots that are colored, and we can make them as accurate as we wish by changing the resolution. Radius 2. Turns out that if you pick a point outside the circle, the loop counts are 0. You pick a point in this area, the loop counts are 1. In this area, red, the loop counts are 2, 3, 4, 5, and so on and so forth. The loop counts are sequential in nature. And that is, as you get closer to the baby, the loop counts get greater, one at a time. And they all can be associated with colors, as I have done here. And when you do that, you get to see the architecture that goes on inside the famous circle of radius 2. Let's take a closer look. We'll call the black covering, we'll call it the cushion. We'll call the red an egg case. We'll call firebrick is the membrane. And we'll call the salmon color placenta. We have outer skin, green, inner skin, and base skin, and other kinds of colors that are sequential in nature based on the loop count as you get closer and closer to the center of the circle. We can continue that on if we chose to. Number 8, loop count 8s are blue. Loop count 9s are navy. 10s are sky blue. 11s are yellow. 12s are orange. 13s are gold, and 14, and we can continue on if we chose. These are the loop counts And these are the colors. And this is the kind of color pattern we get that surrounds the baby. And you can see for yourself the flow of colors here. See the reds and the greens and the blues flowing. As you get down here, you can see, for example, here the magenta flows into a deep pink, flows into a violet and a silver and teal, and it goes on. Question: what do you think would happen if we got rid of all these colors? What do you think would happen if we didn't pay any attention to loop counts 40 and below? What if we were to erase and eliminate and delete all information, loop count 40 and below? What do you think we'd get? We'd get a naked Mandelbrot. We'd get a naked Mandelbrot. We would begin to see the beautiful fractal designs emerge that were being covered up by the surrounding clothes of the Mandelbrot. We can look closer. We can begin to see some exciting fractal patterns that live on the body of the baby. We can look closer at this area. We will. And we can look down here and we can start to see some color develop. That's interesting. But these colors are not the same colors that we saw before. The colors we saw before were 40 loops and below. These colors are perhaps loop 200 or loop 500. Very much deeper into the Mandelbrot. Let's look closer in this area. We see more colors, but again, these are loop counts in the hundreds as opposed to 40 and below. What do you think the loop counts of these little guys here are? Every one has loop counts of 1,000 and greater. Every one of them, because every one of them are set members of the Mandelbrot. Set members. Everything else is loop counts between 999 and 40. And so now you've seen not only the naked Mandelbrot, but you saw what the Mandelbrot looked like with his clothes on. Be sure to go to fractallog.com to see this video, plus its sister video, A Beautiful Equation, which tells you how Mandelbrot, how his equation works in a very simplified way. You'll enjoy it. I hope you've enjoyed this presentation. My name's Dave Fashenpour. Thanks.